Start பண்ணலாம்ல sir?
Start ಮಾಡಿ.
A warm good evening to another present here. A special good morning to our chief guest. I, S. Tamim Nisha, Assistant Professor, DG Vaishnav College, Chennai. It is my pleasure to be a moderator for this wonderful event commemorating 134th birth anniversary of great Indian mathematician Srinivasa Ramanujan. I would like to extend my enthusiastic welcome to all of you. We hope you will learn a lot today. We have lined up for you to be fruitful and engaging. Pi Mathematics Association started functioning as a registered trust from 18 June 2007. We conduct periodical workshops for students of schools and colleges levels and for teachers alike. We also organize lectures presented by eminent professors of international repute to motivate students for higher learning. Pi Mathematics Association has released 14 books in the past 14 years, in which 8 written in Tamil and 6 in English. The book title Engalin Ennangal has been awarded as Best Science Book by Government of Tamil Nadu in April 2017, and it has won one more award for NGO called Pavitram Trust, Chennai. Pi Mathematics Association released a book on Ramanujan on 30th December 2012 commemorating 125th birth year of Ramanujan, the greatest mathematical genius of India. This book has won one award from an NGO called Kavidai Uravu in May 2013. Ramanujan book also has won the Best Book Award from Tirupur Tamil Sangam in February 2014. In all our books has won 8 awards so far. Pi Mathematics Association specializes in presenting mathematics visually to enhance better understanding of mathematics and make learning memorable experience. In this connection, PMA has prepared more than 60 models, has prepared more than to postgraduate level covering almost all branches of mathematics, and these models was enjoyed by many students and teachers of various institutions throughout India. PMA have also conducted summer internship and resource programs in the year from 2016 to 2019. It has also initiated lecture series in mathematics provided by eminent mathematicians to motivate young students and research scholars. One of the main objectives of Pi Mathematics Association is providing educational scholarship for poor and deserving students of any community and race. In the past 14 years since its inception, the association has helped more than 300 students by paying scholarships of nearly 9 lakhs rupees and so forth. In the quest of propagating the beauty and nature of mathematics, Pi Mathematics Association will provide its best efforts in future years. Now, I would like to invite Professor Dr. R. Sivaraman, founder of Pi Mathematics Association, to address the chief guest, Professor George Andrew, Evenpoe Professor, Peninsula Via State University, USA, for this evening. Sir, welcome, sir.
So, good evening to one and all. Professor George Andrews doesn't need any introduction among academic mathematicians and mathematicians, particularly working in number theory, especially in Ramanujan's area, because he is one of the living legends on Ramanujan's work. And he has spent more than 5 decades of his life on researching about Ramanujan's notebooks in collaboration with other great professor Bruce Byrne. So I take this opportunity to give a very short profile of Professor Andrews, who had been inspiration to many throughout the globe, including myself. I remember still that when I was a very young student, I had been to Les Church Road in at Aladi's home, where Andrews used to come there some 25-30 years back. He used to come there and give a lecture during Ramanujan's birth occasion. I got quite inspired by his lectures and got the motivation right from that point until now. So, George Andrews used to say that he got inspiration from Ramanujan. I got inspiration from George Andrews. So, we are very blessed to have you here, sir. And as introduction, George Andrews was born at Salem, Oregon. He received his bachelor's and master's degree from Oregon State University, and he received his PhD degree, doctorate degree, from the University of Pennsylvania. And he is now currently as in the state of Ivan Pugh University Professor at the from in the Department of Mathematics at Penn State University, and he is considered to be expert on Q series, and he has authored Q series, their development and applications in analysis, number theory conference, and he has authored, I hope, at least 10 books minimum, and his books on number theory were quite popular with research people in research circles. Especially his book on theory of partitions is very very well known and very widely read book, and he has a long-term interest in the work of Ramanujan, and he is mainly a person who was remembered very very well in academic circles for his discovery of the lost notebook of Ramanujan in 1976 during his visit to Trinity College. So the people were working on lost notebook contents right now. So the whole body of research were going on lost notebook, courtesy to Professor Andrews' effort of discovering the lost notebook. He has written and published more than 300 high quality papers. I think when I saw last time it was around 356 or around 360, so more than 300 definitely, and they were very high quality, and the number of citations in Google Scholar and Scopus were in thousands actually. So you can see the amount of interest and things that are generated from his work is huge actually. So he's one among the best in the business, and he has served as thesis advisor and research guide for more than 40 students in guiding PhD and master's degree. George Andrews was elected in the American Academy of Arts and Sciences in 1997 and to the National Academy of Sciences America in the year 2003. He was awarded honorary doctorates and honorary professorship at Nankai University in 2008. In 2009, he became a Siam Fellow. He holds honorary degrees from the universities of Parma, Florida, Waterloo, Illinois, and during the 125th birth occasion of Ramanujan, Bruce Bund, and other dignitaries were Richard Askey, if I remember correctly, were given honorary degrees at Sastra University, Kumbakonam. That was a very great occasion. And Professor John Andrews had been served in very very important position that includes President of the American Mathematical Society during the period from 1st February 2009 to January 31st, 2011. So for the 2 year period, and I remember in the year 2010 when ICM was going on, he was here at Hyderabad when ICM was during his tenure. ICM took place in India, and he was very supportive to us also. And he subsequently became fellow of the American Mathematical Society in the year 2012. You are really a person who motivates everyone and inspires. Not only that you got motivated from Ramanujan, but you inspired me and several people in India. So we are very happy to have you here and provide a lecture. With this few words, I welcome Professor Andrews to provide his lecture. Thank you.
Thank you. So now I need to share the screen. Okay. So I hope you can hear me. So it is a great honor to participate in this event, which is honoring the 134th birthday of Ramanujan. The talk that I'm going to give is actually in honor of Hansraj Gupta, and I think it is completely appropriate to give such a talk on this day because Gupta, during the middle part of the 20th century, was perhaps the main person in India or in the world who was contributing to and looking after the work of Srinivasa Ramanujan. So here is a picture of Professor Gupta. Professor Gupta visited me in Penn State University in 1974. He, at that time, looked to me like a very old man. He was actually probably 10 years younger than I am now, but he had been on a long flight to North America, and by the time he got to Penn State, he was very tired, and I wondered how in the world he would be able to give a talk the next day. But to my great and grand surprise, he gave a beautiful lecture on mathematics related to Ramanujan. And as I was leaving the hall that day, someone said to me, that's the sort of lecture that ought to be a standard colloquium talk. So Kansraj Gupta was my friend, and I honor him in honoring Srinivasa Ramanujan. In maybe 10 or so years ago, it was decided that the collected works of Hansraj Gupta should be produced, and they are now in print in 4 volumes. And I was asked to provide a short article in tribute to Professor Gupta. It was mostly about my relationship with him and about his mathematics, but I did want to say something about mathematics that was new, that was related to his ideas. And what occurred to me, because I'd been looking at a related problem, was something that I've called the method of foreshadows. So this is a very elementary theorem in mathematics, extremely elementary. And I want to tell you about it and to tell you of the surprising discoveries that have come as a result of this result. So the lemma you see on the screen is called the mod 4 lemma. So you suppose you have f of z, which has a power series in z, and the coefficients might be power series and other variables, all with integral coefficients. The assertion is that modulo 4, all the coefficients of the square of this are congruent to the coefficients when you replace z by minus z. So this is very easy to prove. Here's the proof. If you take f of z squared minus f of minus z squared, obviously by the familiar factorization from elementary algebra, it's these two factors, f of z plus f of minus z, times the factor f of z minus f of minus z. This latter expression is twice the even part of f of x times twice the odd part. 2 times 2 is 4, and there you have the mod 4 lemma that you saw in the previous screen. And I would note, although it will not be of importance in this talk, that you can extend this idea to higher powers of 2. So in particular, the generating function for the number of partitions of n, which you see at the top of the screen, and at the bottom of the screen, you see the definition of this, what is called the Q-Pochhammer symbol, A semicolon Q sub n. So that will occur throughout this talk. So I want you to pay special attention to that definition. It's just the rising factors, 1 minus a, 1 minus aq, etc., up to 1 minus aq to the n minus 1. And of course, you can let capital N tend to infinity, and the generating function for the number of partitions of n is given by this infinite product that is listed at the top of the screen. And so I do just a little algebra on it, multiplying numerator and denominator by q infinity. And then you can legitimately replace q by minus q in this squared term. And this is true mod 4. And once you simplify things out, you have 2 of Ramanujan's famous functions, his phi of q, which you see defined at the next line at the bottom of the screen, and his psi of q, which is also defined on that line. Phi probably goes back to Jacobi, and psi goes back to Gauss, but Ramanujan used them so extensively that I will use Ramanujan's notation for both phi and psi. The formula that you see here, mod 2, is one that Professor Gupta used to determine the parity of P of n for, I think, at least up to n equal 1,000. Keep in mind, excuse me, keep in mind that Professor Gupta was working in the early part and middle of the 20th century before one had access to high-speed computers, so that he computed many tables of partitions through hundreds of values, and it was all work that was done by hand. Well, this same idea can be applied to what are called two-color partitions, where you square the generating function for ordinary partitions. And again, you can replace q by minus q. And then you work through a few algebraic manipulations of these infinite products. And what you have at the bottom of the screen is the Ramanujan psi function minus q quantity squared times the p2 of n with q to the 4n. So again, you have a similar formula. Here was one related to what Professor Gupta did with regard to the ordinary partition function. And here you have one excuse me, mod 4, related to this partitions with two colors. So where did I run into this mod 4 lemma? Obviously, it's very easy, but why would you think of it in the first place? So the answer is studying Ramanujan's Mach theta functions. So I have two functions here, capital P of Q and F of Q. Capital P of Q has this formula that you see on the third line of the screen, which is this infinite product. And Jacobi showed that this infinite product was equal to the infinite series, where you have q to the n squared in the numerator and qq sub n quantity squared in the denominator. Ramanujan, for reasons that I have talked about in other talks, discovered the Mach theta functions. These are functions that behave in their analytic way very much like the ordinary theta functions, which transform in beautiful ways under the actions of the modular group. He wanted similar functions that would behave at least almost as nicely as the theta functions. And the things he found, he called Mach theta functions. And indeed, the f of q you see in the middle of the screen is one of his Mach theta functions. G.N. Watson, studying Ramanujan's work, showed that the Mach theta function is equal to basically P of Q, this 1 over QQ infinity, times this series with 1 plus 4 times this expression you see there. In other words, if you look at the top of the screen, the bottom of the screen establishes what is at the top of the screen, namely P of Q is congruent to F of Q modulo 4. Well, what I wanted to know is there a Watson's theorem at the bottom of the screen is really difficult to prove. I mean, this is a major accomplishment in order to prove this congruence at the top of the screen. And I wanted to see if there was a simpler way, an elementary way of establishing this. And the answer is yes. In fact, if you look at the denominators of P of Q and F of Q, you see that all you're doing is changing the sign in the denominator. And if you think of these two things as functions of z, the mod 4 lemma tells you that this congruence is true. And then you set z equal to 1, and you have the thing that's on the previous screen. And you do not have to go through any of the very difficult mathematics that G.N. Watson went through to establish this same theorem. The new function that arises after the use of the mod 4 lemma, we will call a foreshadow. And the difference between the original function and the foreshadow divided by 4 will be called the shadow difference. For example, P of Q minus F of Q divided by 4 gives us this shadow difference, this Appel-Lerche series for the shadow difference. So one of the things I wanted to do was to see if there were other theorems like this that arose, and some very surprising things happened. And those are what I want to tell you about in the remainder of this talk. So the first thing I start with is what is called the generating function for over partitions into parts not divisible by 3. And basically, it is another infinite product. The thing to be aware of is its generating series 1 plus 2q plus 4q squared plus 6q cubed dot dot dot. Lucy Slater, who was a student of W.N. Bailey, who was one of the mathematicians in England that carried on the study of Ramanujan's work, Lucy Slater proved that theta of 3 is this rather complicated looking expression. But the neat thing about it, don't get too distracted with all of the material in it. Just look at the fact that in the numerator of this series, there is one of these finite products squared. And so for the same reasons as dealing with P of Q and F of Q, we can remove that minus sign and we obtain the obvious foreshadow. And owing to the two preceding sums, we take as the shadow difference divided by 8, because the preceding sums both had 2 out in front. So when we divide by 4, that really doesn't cover the congruence adequately. So for the foreshadow, shadow difference, we're going to divide by 8. And what is this? Well, here you have the power series expansion for this shadow difference of these two functions that are developed from the work of Lucy Slater. Well, anytime you have a series with integer coefficients, almost everybody in this business runs to the online encyclopedia of integer sequences to see if it's there. And unfortunately, this is a little too small, unless your screen is bigger than the one I'm looking at, for you to actually see that this sequence, which is listed here, is identical with this out through the first 21 terms. In other words, it starts out with a whole bunch of zeros, and the first one occurs at q to the 5th. And then 1, 1, 3, 4, 7, 10, 1, 1, 3, 4, 7, 10. So, but it stops being true out of 23 terms. So what I wanted to do was to find out what's going on. So the first thing I did was to notice that Clark Kimberling is the author of this page. So I wrote to him and I asked him what indeed is happening here. Could he tell me what the generating function is for this? And unfortunately, he had no information on that. He just had used the Mathematica software to construct these partitions, where he was taking the largest part minus the number of parts minus the smallest part. And so I've called that the Kimberling index. And so what I needed to do was to see what the relationship was between this theta 3 bar and the series that Clark Kimberling had come up with. So what I was able to do was to show that this theta 3 bar is equal to this series. It basically follows from something called the Bailey chain and Bailey pair argument. But what you see is basically a series that is very familiar in theta series work, where there's this 2n squared minus 1 thing out front, and theta 3 is equal to that, so that, as you see at the bottom of the screen, d3 of q is equal to 1 over q infinity times this series with this rather complicated expression divided by 8 inside the sum. I should mention just in passing, although this is more for the experts watching today, that the theorem that I proved at the top of the screen, theorem 1, follows from a weak form of Bailey's lemma, where you have two sequences, alpha n and beta n, and if they are related by the relation you see here in Bailey's lemma, then the infinite series identity follows. And in this case, the Bailey pair is precisely the one I need in order to make the theorem provable. And we, as I mentioned earlier, we're faced with the mystery of the relationship between the coefficients d of q and this A237833 in the online encyclopedia of integer sequences. So here's the message I actually wrote to Kimberling. I would assume you have a useful formula for the generating function for A237833. However, it's not listed on that page. You notice always when you visit the online encyclopedia, they have not only the sequence listed, they have lots of references, they have software references, they have related sequences, they have all sorts of stuff. But on this, many times they list a generating function, but that was not listed. And so I asked Clark Kimberling if I would be grateful if you could supply a reference. Here's his response. The sequences you mentioned were found by computer. I don't have a generating function, and as far as I know, the sequences have not appeared previously. So here's what I call now the Kimberling index, which I mentioned earlier. It's the largest part minus the least part minus the number of parts. And I'm going to look at the Kimberling index where it is greater than or equal to 0. So here you see an example of computing the Kimberling index. It's if the partition is 11 plus 7 plus 7 plus 4 plus 3, excuse me, the Kimberling index is the largest part minus the smallest part minus the number of parts, or 11 minus 3, the smallest part, minus 5, the number of parts. So the Kimberling index in this case is 3. So you can define 5 partition functions depending on whether the Kimberling index is greater than 0, less than 0, less than or equal to 0, greater than or equal to 0, or equal to 0. And here are 3 equations which are trivially true just by the definition of less than, equal, and greater than. And so if you have the generating function for any 2 of the Kimberling functions, then the above formulas yield generating functions for all 5. Whoops. I'm touching too many keys at once. So to treat the generating function for k less than or equal n, we need this. So what I'm really interested in is k greater than or equal to n, but I'm listing only k less than or equal to n. And I need this famous Q binomial coefficient, which is the generating function for partitions where each part is less than or equal to n, and the number of parts is less than or equal to m. And I need a formula which is in its full generality due to Nathan Fine, but in fact appears with A equal 1 in Ramanujan's Lost Notebook. And that is this Q of A semicolon Q function is this fairly nice series, and it's equal to another series which looks very much like this infinite product times a theta series. So the qk less than or equal function I want to prove is equal to this expression that you see here. So how does the proof of that go? So instead of dragging you through the weeds, let me give you a generic proof. I'm dealing with Kimberling's less than or equal function. And so I look at a Ferrer's graph of a partition where I have an n by n rectangle, with n being the number of parts, m then being the smallest part, and then I tack on this sort of triangle of nodes for the rest of the partition. And so you see there's a triangle, a rectangle that has m by n nodes in it, thus producing this q to the nm that you see there on this, that you see there on the screen. And then this Gaussian or Q binomial coefficient generates the nodes that go into the triangle. And so I fill that in. Then I sum on M, which is just a geometric series. And then I use this formula that I had for the Q to get the K less than or equal series to look like that. So, and then I can't use Q directly. I have to use a difference of values. And the difference of values you see at the bottom of the screen after appropriate algebraic manipulations. And to obtain the second expression in theorem 2, what is the second expression? There you see a very nice looking thing with the n q to the n times 3n minus 2. With that expression, you differentiate with respect to A, because when you differentiate with respect to A, you see that the power drops down and you get the n that you want. If you look at the top of the screen here, differentiating with respect to A is where you get that factor. And you set A equal to 1 and you have this theorem. And that's K less than or equal to. And so K greater than is going to be given by that expression, because it's the complement of it with respect to the partition function. So now here's what we have. We have D3 of Q. I obtained that series earlier utilizing the Bailey lemma. And you see what's here. It starts out, it has this infinite product out front, and then it has this very lacunary series inside parentheses. Most of the coefficients are 0. There's q to the 5, q to the 7th, 2q to the 15th, q to 2q to the 17th, and 4q to the 22. Whereas at the bottom of the screen, you see this k greater than n is exactly the same thing until I get to q to the 22, at which time the coefficient is not 4 but 3. And that explains the mystery of this discrepancy between the thing that we'd found using the foreshadow idea and Lucy Slater's series and this empirical work done by Clark Kimberling. So that's the first mystery that arose from the foreshadows that is solved by a mixture of partition theory combinatorics and the methods of W.N. Bailey and L.J. Rogers. So, being very pleased with the success of this approach to reveal number theoretic mysteries, I moved on in Lucy Slater's list. And this is the next formula I came to, which is rather like the previous one, except that in the previous one, instead of the psi function with q cubed in the numerator, there was the phi function with q cubed in the numerator. And so I thought, what a perfect symmetry this is. And so obviously there's an obvious foreshadow choice. Namely, you can change the sign of things in the numerator. And I see that I have done a fair amount of algebraic manipulation here so that you don't see explicitly. The first thing I did was to change the q in the numerator, the minus q in the numerator, q in the numerator, and then one of the factors in the numerator cancels into the denominator, which is where you get the second expression on this page. And surprisingly, this is the generating function for 3 regular, for Yes, three regular partitions, which arises in the, the representation theory of the symmetric group. So all of a sudden, just using the foreshadow, we touch another branch of mathematics, namely representation theory. How does the proof of this go? Well, not surprisingly, one I should mention that Lucy Slater's list of these formulas, she has a large paper called Further Identities of the Rogers-Ramanujan Type, which was published in 1952 in the Proceedings of the London Mathematical Society. And it is basically her PhD thesis written under W.N. Bailey. In this paper, she has 120 formulas, and this is what I've been looking through to try to find formulas where there is, say, a square in the numerator, as you see in this identity, and thus leading to the application of the foreshadow method. So she proved the formula that you see on this page using the Bailey lemma that I described earlier. And so what I did was to replace her beta with the beta related to this C bar. And by doing that, you get the series that you see at the bottom of the screen. And the nice thing, of course, is that the series that is in the next to last line, this is a famous series. It's originally due to Jacobi, and it's just the cube of Euler's infinite product. And you see, it's generally written in the base q, but as you see, this is in base q cubed, and so that's why you see the q cubed throughout the numerator of this expression. Thus, for the shadow difference, we need to take the difference of C and C bar and divide by 4. In this case, there is no spurious 2 out front, so we divide actually by 4 for the shadow difference. And what we get is this, and I've written out the first 18 terms of this series. Well, everybody watching knows exactly what I'm going to do next. What I do next is to say, how interesting here is this infinite series of integers. I wonder if it appears in the OEIS. So I turn to the OEIS, and lo and behold, the same thing. Here are first 2 zeros at the beginning, then 1, 1, 1, 1, 1, 2, 3, 5, 7, 10, 20. It's right there, 5, 7, 10, 20. But right at the 18th term, it's not 148. I think it's 147, or maybe it's 149. In any event, it breaks down, but it coincides for a very long way. And so now I will ask myself, well, what's going on here? And of course, the nice thing about the OEIS is that it gives you references. And excuse me, I need to take a drink of water. One of the references is to my colleague in the mathematics department at Penn State and my close friend, James Sellers. And it's related to what is called Bulgarian solitaire. So this was a hugely popular mathematical puzzle maybe 20, 30 years ago, first introduced to the world by Martin Gardner in the Scientific American in his famous column on mathematics. Basically, it's a very simple idea. You take a deck of n differently numbered cards, and you place them into piles. And once you set a number of piles out, then you take one card from each pile and create a new pile. And you then do the same thing again and again, taking a card from each pile and creating a new pile. And what happens? This isn't exactly what one would call one of the great exciting solitaire games in the history of solitaire games. What happens eventually is as follows. Well, first of all, what happens eventually is that if n is a triangular number like 1, 3, 6, 10, 15, 21, etc., then what happens eventually is that you get a set of n piles with one card in one pile, two cards in the second, three cards in the third, etc., up to n cards in the nth pile. And as you can see immediately, when you remove one card from each pile, you get a new pile that has n cards in it, and the preceding piles have dropped just by one, so you have exactly the same arrangement that you have before. In other words, you're in a steady state circumstance. Nothing is ever going to change again when you go through this process. If you have anything other than a set of n cards, you never get to a steady state. You basically get to some sort of recycling business. And so the problem was to prove that the steady state only occurred with triangular numbers. Eventually, this problem was solved. For the talk this morning, what I want to emphasize is that Bulgarian solitaire can be viewed as a game played on partitions of n, and some of the partitions of n have no pre-image. In other words, you view those piles as the number in each pile, and that gives you a partition of the number n. And when you go through the game, new partitions arise. But the question that Sellers and Brian Hopkins asked themselves were, are there partitions that, unless you start out with them, they will never occur again? They will never arise. Subsequently, they have to begin at the beginning of creation. And of course, the biblical story about humanity being created in the Garden of Eden. So we have these partitions supposedly created in the Garden of Eden because they never arise subsequently in history of this game. So Hopkins and Sellers showed that the Garden of Eden partitions are exactly those with rank less than or equal to -2. What is the rank of a partition? It's the largest part minus the number of parts. Remember, the Kimberling rank was the largest part minus the number of parts minus the smallest part. So the most famous rank was created by Freeman Dyson, and it is the largest part minus the number of parts. And what Hopkins and Sellers showed is that the Garden of Eden partitions are exactly those where the rank is less than or equal to -2. And from this observation, they were able to prove this generating function. And as you can see, the generating function there looks a good deal like the sort of thing that you see here, namely this 3n choose 2 in the generating function for delta 3. And so this will be the source of our study. So consequently, the Garden of Eden partitions are of this nature, namely the series that Hopkins and Sellers had. If you expand it out, it looks like that. Whereas the series for delta 3 of Q, which is right back here, delta 3 of Q has this much more complicated expression involving -1 to the n times 2n plus 1. But the first two terms are identical with those two terms. And of course, the quadratic nature of the exponent, so this is 3 times 6. 18 is 3 times 6. You're 3 times 1, 3 times 3, and 3 times 6. And so that's where the discrepancy arises at q to the 18th. So there's one last observation, namely, we note that the Garden of Eden partitions G E of n equals the number of partitions of n in which the first missing multiple of 3 is even. And so I want to explain why this is true. This is just a corollary of this study. So when n is equal to 7, the number of Garden of Eden partitions is 5. So the rank is, if these are the 5 partitions of 7 that have ranks smaller than or equal to -2. For example, the first one you see is 3 plus 4 ones. So the largest part is 3, the number of parts is 5, 3 minus 5 is actually equal to -2. And at the bottom, you have the number of partitions in which the first missing multiple of 3 is even. So you can't have you can't use 6 has to be missing, and that is what you see. You could use the partition 6 plus 1 because then the first missing, or you couldn't. You have 4 plus 3 ones. So what you have are these 5 partitions where the first missing multiple of 3 is even. And why is that true? Well, you have to take apart the Hopkins and Sellers series and rewrite the even terms and the odd terms. And if you rewrite the even terms and the odd terms, and then expand this binomial coefficient 2n choose 2 into the sum of the first 2n minus 1 integers, you see immediately, as we go to the bottom of the screen, that the nth term here is generating partitions where 3 appears, 6 appears, 9 appears, etc., up to 3 times 2n minus 1 appears, but 3 times 2n does not appear. And so consequently, you have the theorem that we showed right here. Wait a minute, where did I miss this? Namely, G of n equals the number of partitions of n in which the first missing multiple of 3 is even. All right, so that pretty well covers what I wanted to say. I wanted, on this day honoring Ramanujan, to honor a man who honored Ramanujan, and he honored him in a singular way by doing mathematics. Much, if not the majority of his work, is closely related to Ramanujan's work. His own contributions have been many beyond what I mentioned today. For example, the modification of Ramanujan's congruence conjecture was first discovered by my former colleague Sarvadaman Chawla, when he, looking at Gupta's table, observed that Ramanujan's congruence was not quite true at power of 7 cubed, and thus was modified in a way that G. N. Watson was able to prove it in the late 1930s. So I hope you have gained not only some information about the world that Ramanujan worked in, because everything I've described this morning is out of the Ramanujan world of mathematics, but also you've gained some appreciation of my old friend Hansraj Gupta, who contributed so much to keeping the memory of Ramanujan alive. Thank you very much for your attention.
Thank you very much, sir, for your interesting lecture. And we received a lot of information from your speech. Thank you very much.
Thank you.
Now the session is open for question and answer discussion. If anybody have any questions, he would be pleased to answer them. Any questions? Any queries? Vijay Kumar, sir?
Any questions in the chat box?
No, sir. Still, there is no question in chat box. Sir.
Okay. So then I need to ask one or two couple of questions to you, sir, before we close, sir.
Please proceed.
Good.
So I was actually getting thrilled whenever I could prove what little with my knowledge in Ramanujan's equations from his notebooks, jottings, or what little I think. And you have devoted your whole life, almost more than half your lifetime, to involving Ramanujan's area. So how much happiness that you derive in proving his theorems and formulas?
So I should say to everyone listening, if you can have a career in mathematics, it's the greatest job in the world. The thrills are numerous and of a variety. Discovering why one of Ramanujan's formulas is true is a great is a great thrill. Finding a new application of one of his formulas is a great thrill. Teaching his work to others so that they see the beauty of it is a great thrill. This is a life that is filled with beauty and enjoyment, and I recommend it to anyone who finds mathematics interesting and who has worked hard and achieved in it.
Okay, sir. So thanks, sir. And what do you think that what lies ahead in Ramanujan's works in future?
Well, so new things arise every day. Uh, the Mach theta functions, which he discovered in the last year of his life, which constitute a large part of the Lost Notebook, are a hot topic of research right today. New ones are discovered regularly. New applications are discovered regularly. The theory of partitions, to which he contributed so much, is constantly uh, obtaining new discoveries. One of the nice things to be alive today is that we have the power of modern computers and modern computer algebra, so that while many of us are far from being able to compute and to see as well as Ramanujan did, we do have the advantage of these powerful machines which can do such tremendous computations and thus illuminate aspects of Ramanujan's work that could not possibly be considered or illuminated during his lifetime. So this is a great time to be alive and a great time to be working on mathematics.
Thank you, sir. Thanks for your thoughts.
You're welcome.
With your permission, shall we share the messages by three people, sir?
I'm happy to share anything. Yes.
Yes. Vijay Kumar, please share. Vijay Kumar? Vijay Kumar, can you share? Vijay Kumar?
Sir, I'm sharing, sir. It's not showing, sir.
They're not coming here. Only empty screen is there. Please share your that presentation.
Oh, okay, sir.
Come from the first line. Yes.
Now it's okay, sir.
Yes, yes, yes. Go to the first slide.
This message by Bruce Burns.
Go to the second slide.
This message by Michael Walsmith.
Go to the third slide.
This message by Professor Srinivasa.
Okay. Okay, thanks, Vijay. You can close it. So, on behalf of our association, we thank you very much, sir. Anyway, we'll have a formal vote of thanks. And we are, as I said, you continue to inspire us right from my young age, and my followers will also follow you for sure.
Well, thank you for inviting me to participate. It is a great honor, and I'm very pleased to have been involved. Thank you very, very much.
Thank you, sir. We will now have formal vote of thanks. Madam, invite Kalyan Kumar.
Yes, sir. Thanks for your enthusiastic participation. May I call on Mr. V.R. Kalyan Kumar, member of Pi Mathematics Association, to kindly deliver his vote of thanks. Sir, please.
Yeah, thank you, madam. So, on behalf of Pi Mathematics Association and all the participants, I'd like to sincerely thank Professor George Andrews for providing his valuable lecture and spending his valuable time with us today. We sincerely thank you, sir, for the informative lecture provided today. So, we had an opportunity to know more about Professor Hansraj Gupta. So, we thank you for that. And we also we are able to feel connected. This lecture has provided us with one more opportunity to connect with the life and achievements of Srinivasa Ramanujan. So we are glad and we thank you for that, sir. So thank you for providing us with information on critical topics like Q series, foreshadow method, Kimberley index, Bulgarian solitaire, and Garden of Eden partitions. So we will take inputs from your session, sir, and then we will work forward on that. Thank you. Thank you so much for that. So I have no doubt that all the participants and students in today's lecture, they will take this session as a starting point, and they will do some more research with the valuable information provided to us, sir. So we thank you for that.
Thank you.
Yeah, and I would like to thank all the members of the Pi Mathematics Association for arranging this informative session. I would also like to thank all the students, faculty members, and all the participants today for joining this session and giving their support. And today, as Vijay Kumar sir has shared, we have received messages from eminent professors across the world. So I would like to sincerely thank Professor Bruce Burnt, USA, Professor Mitchell Walsmith from France, Professor K. Srinivas from India, for sharing their messages on this occasion of 134th birth anniversary of Srinivasa Ramanujan. Finally, I would like to thank Professor Tamim Nisha for comparing today's session. And I would like to share a message that Pi Mathematics Association will be uploading the recorded version of this session in the Pi Mathematics Association YouTube channel. So if the participants want to refer to the contents later, they can feel free to reach the recorded session by referring to the Pi Mathematics Association YouTube channel. Once again, I thank you all for providing me this opportunity. Thank you.